Today's tape only involves two major concepts, that of transpose and that of a symmetric matrix. I'm not introducing too many concepts too early because I want to give you a chance to get used to the idea of proving the concepts and proving the properties. So today's lesson is going to concentrate again on proofs, the method of proofs. Basically, the early proofs involves taking an expression, expanding it by using the definitions, making the required change, and then translating back. And we will do some proofs of that type in today's tape. The transpose of a matrix is a matrix that results from interchanging its rows and columns. So the transpose of a matrix is a matrix that results from interchanging its rows and columns. The transpose of matrix A is denoted by A with a T. So if you see the symbol, that's read A transpose, or the transpose of matrix A. Let's look at an example. A is the 2 by 3 matrix. 1, 2, 3, 4, 5, 6. So notice A has rows 1, 2, 3, 4, 5, and 6. Now if I were to write the transpose, A transpose would be interchanging the rows and columns. So the columns of A transpose would be 1, 2, 3, would be column 1, 4, 5, 6 would be column 2. So the rows and columns would be interchanged. So here is A transpose. And notice A transpose becomes 3 by 2. Again, if you have 2 columns, 2 rows and 3 columns, and you change it, then you're going to have 3 rows and 2 columns. So notice column 1 becomes row 1, column 2 becomes row 2, column 3 becomes row 3, or row 1 becomes column 1, row 2 becomes column 2. The transpose is very important because in some instances we could not multiply by matrix A because the dimensions didn't match, but we might be able to multiply by the transpose. Let's look at some of the properties of transposes. Let A and B represent matrices and C represent a scalar. In other words, C is a real number. The transpose of A transpose is A. So that's pretty logical. Just think about it. I start with A. I interchange the rows and columns. I get A transpose. Now if I interchange the rows and columns again, I'm back to A. This one is not quite as obvious. A plus B transpose is equal to A transpose plus B transpose. So I can add A and B and take the transpose and get the same answer as if I take the transpose and then add. If I multiply the scalar times a matrix and take the transpose, I get the same result as I would if I take the transpose of the matrix and then multiply by the scalar. if I multiply two matrices and take the transpose, I get the same answer as if I take the transposes and then multiply. But notice I've had to change the order here. It's no longer AB, it's BA, because now the dimensions would not match otherwise. So I have to fix it so the dimensions would match. Well, let's go ahead and prove 4. That's the hardest one. So let's start with A times B transpose. Well, let's just use the definition for A times B. And I could say that would be matrix Aij, matrix Bij, transpose, because I can denote matrix A by the set of all elements included in its ith row, jth column, and B the same way. Now look back for matrix multiplication. And from the last, actually we did work with this in the last proof. This would be A, I1, B, 1J, plus A, I2, B, 2J, plus, and it goes out to A, IN, B, N, J, transpose. Now what happens when we do the transpose? We interchange the I and the J columns. We interchange the rows and the columns, so that means we're going to interchange the I's and the J's. So when I do the transpose, it's going to be A, 1, J. See, in place of the 1, I'm going to have to switch rows and columns, but rather than being I, it's going to be column J, and it's going to be B, I, 1. Plus, we're interchanging rows and columns, so it's going to be A, 2J, B, I2. Plus, it's going to be A, N, J, B, I, N. So that's taking the transpose. Now these are real numbers, so this is going to be B, I1, A, 1J, plus B, I2, A, 2J, B, IN, A, NJ. And we recognize this as being the B transpose times the A, IJ transpose, which is B transpose A transpose. Now let's prove one that's not quite as hard to see. I want to prove one that was, would kind of challenge you. Let's prove property 2 now. I've already basically talked through the proof of 1. Let's look at A plus B transpose, and let's show it's the same as A transpose plus B transpose. Well, A plus B transpose is going to be the same as the matrix of Aij transpose, plus the Bij transpose. By doing this, this would just be Aij plus Bij transpose. Well, to do the transpose, I interchange I and J, so it's going to be A Ji plus B Ji. Well, if I've interchanged the columns, this is going to be A Ij transpose plus B Ij transpose, which is A transpose plus B transpose. So that was a little easier to follow. Here's another important concept in matrix theory or linear algebra. If A is equal to A transpose, then A is symmetric. If A is equal to its transpose, then A is symmetric. Let's look at the matrix 1, 2, 3, 2, 5, 4, 3, 4, 7. So this is a matrix. Let's do the transpose. The transpose is when I interchange rows and columns. So what is row 1 in matrix 1 becomes column 1 in the transpose. So it'd be 1, 2, 3. So 2, 5, 4, 3, 4, 7. You say they're the same. So that's how I can tell they are symmetric. A is the same as its transpose. Now another way of looking at symmetry is look down the main diagonal and see if they're the same on both sides. So look down the main diagonal and look to see if it's the same. 2, 4, 3, 2, 4, 3. If you were simply to bend it over, the 3 would bend onto the 3, the 4 onto the 4, and the 2 onto the 2. That's really where the word symmetric comes from. Let's play with derive a little bit, or I'll let you go into the math lab after you get through viewing the tape to play with this. Let's use derive to evaluate A transpose for A is equal to 2, 3, 1, negative 2, 10, 1. So we want to use derive to evaluate A times A transpose. Well, before we go to derive, let's see that we can do it. If I do A transpose is going to be row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. And we see that we can multiply because this one is 3 by 2, this one is 2 by 3. So I can do it. The first step will be to enter the matrices. Well, to enter the matrix, remember you choose author, you choose matrix, and you give the dimensions. So all we're going to have to enter is A. So enter matrix A, which is a 3 by 2 matrix. So click on your arrows until the dimensions read 3 by 2. I told you wrong a while ago. It's 3 rows, 2 columns. So it's a 3 by 2 matrix. Now once you get the matrix entered, you choose author and you type number 1, because that's the only matrix you've entered, times, remember the period means times for matrices, number 1, and this is the symbol for transpose and derive. So find this symbol on the keyboard, and this is your symbol for transpose on derive. So this is A times A transpose, because expression number 1 is matrix A. A times A transpose. And then you simply choose simplify and choose basic. Author the matrix. I tell the dimensions to be 3 by 2, and then I'm doing matrix A times A transpose, and we get the answer. Now notice something about the answer. If we were to draw the diagonal through here, it's the same on both sides. The negative 4 return to the negative 4, the 23 into 23, the 8 into 8. So we see that it is symmetric. You may wonder, is that always true? Well, of course, an example never proves anything, but we might think that it would always be true. But we did notice that the answer was symmetric. So we have the answer to that problem, at least, is symmetric. We might think it's always true. Can we prove that A times A transverse is a symmetric matrix? Well, really we can. We can prove that it is a symmetric matrix. And what we must show is that A times A transverse is equal to A times A transverse transverse. Because that's how you show the matrix is symmetric. The matrix is equal to its transverse. So this matrix is equal to its transverse. Well, this proof is really pretty simple. We know that A times A transverse transverse is equal to A. Now we see we had to switch the order here, so it's going to be A transverse transverse times A transverse. That's the one I proved for you. A times B transverse is equal to B transverse A transverse. So your B is kind of like A transverse. So it'll be A transverse transverse times A transverse. B transverse A transverse. But property 1 tells me that the transverse of A transverse is just A. So I have A times A transverse. So I've shown that the transverse of A times A transverse is itself. So therefore, anytime I multiply A times A transverse, I will get a symmetric matrix.